Hey, it's Jim, and this is level 1 of the CFA program, the topic on quantitative methods, and the learning module on probability trees and conditional expectations. Let me read the first sentence in this learning module to you, at least the first part of it. Investment decisions are made under uncertainty. Wow, what a mouthful that is. Let me quickly remind you that in the previous learning module, we had great conversations about lots of things, but in particular, standard deviation, skewness, and kurtosis. These are great measures of dispersion, and consequently, they become great measures of risk. So what we did in that previous learning module is we laid a really good foundation. Now we're just adding to it. We're going to add the essence of looking to the future and estimating probability of outcomes. And how does that contribute to our understanding of dispersion? And here, look at the first LOS. We're going to go ahead and do expected value, variance, and standard deviation, just like we did in that previous learning module, but we're going to add the specter of probabilities. Second LOS, we'll look at a probability tree. And then the third LOS, we'll look at the Reverend Thomas Bayes formula. What these three LOSs are going to do is simply add to our base of knowledge, contributing to our understanding of risk management. Let me read that first sentence to you again. Investment decisions are made under uncertainty. Boy, we've got lots and lots to talk about. It's going to take us all the way through level 3 to kind of dissect and digest that super simple sentence. All right, that first LOS, we've already done this, but we haven't done it with probabilities. So all we're going to do is we're going to say, all right, we have a potential outcome in the future that we can assign a probability to. And then we have another potential outcome. Maybe it's just a simple binomial distribution where the firm can either increase its dividend or decrease its dividend. And then we attach probabilities to those. So look on the blue box on the far right of the equal sign. There's a summation sign. All we're going to do is we're going to take each individual possible outcome and we're going to weight it by its probability. So look at that first diamond point up there. What's the definition that we've given you? Is the probability weighted average of the possible outcomes of a random variable, like stock returns or maybe even dividend yields. So remember what I said to you back in that previous learning module, that the expected value, also known as the mean, also known as the point of central tendency, also known as the average, that's the first moment of the distribution, which implies that there is a second moment of the distribution, and that, of course, is the variance of that random variable. So the question then becomes, how do we take the computations that we did in the previous learning module and add them to this probability weighted? Well, we're going to do the exact same thing that we did before, and we're going to couple it with the blue box. So look down at the orange box. We're going to take each individual outcome. Notice there's an X1 and an X2, and we're going to subtract the expected value of that outcome. Then we're going to square it, and then notice we'll multiply it by the probability. So this is a probability weighted average again. Now, I always ask my students, why do we square the difference between those two? Now, I probably said this back in the previous learning module, but I think it bears repeating. Here's the example that I give my students in my class. Now, I teach in the finance trading lab, and so I have the board behind me, and my students are sitting in 2 rows on either side, so I have an aisle. So I walk up and down the aisle, and we have monitors on that side, so I can walk up and down. And I look this way and I look that way. So I say to them, I say, hey, look, let's play a game. Let's play a game called Count the Number of Steps That Jim Takes. If I stand in front of them and I go, 1, 2, 3, 4. So I look at them and I say, how many steps did Jim take? And they, of course, look at me like I'm some kind of a cartoon character. And they go, all right, Jim, we'll play along because we love finance and we love the statistical application that you can use in finance. They say 4. So I go back to the front of the room and I say, all right, let's play the same game. But what I want you to do now is I want you to close your eyes and close your ears. And of course, most of them don't play along like that. So I say, all right, ready? And I tiptoe. I go 1, 2. And I turn around and I go, 1, 2. Then I turn around and face the class and I say, how many steps did Jim take? And then I say, how many steps does it look like Jim took, right? And I said, for those of you who played along, it looks like I didn't go anywhere. You want to say 0. But everybody knows that I took 4 steps. I just put them in one direction and I turned around and came right back from that same direction. So the reason that we square the difference between each possible outcome and its mean is to get rid of the negative, but also to be able to accurately count the number of steps that Jim takes. You see, statistics is your friend. If you understand this quantitative method stuff, you will be a much better financial analyst and you'll have a higher probability of passing the exam. All right, so thank you for bearing with me there. Now, my wife never asks me to go to the food store and get 12 squared pounds of potatoes. So the variance is in a squared term, a squared unit. So we need to take the square root of that, just like we did in the previous learning module. So that's the standard deviation. Look at that embedded diamond point there. If the variance is 0, there is no dispersion, which means that there is no risk. This is super, super important. Now, when the variance is positive, which it will be for almost all financial securities out there, with the exception of a treasury security, of course, then it signifies a dispersion of outcomes. So the higher the variance, the higher the standard deviation, that means the greater is the risk. And that's super important as we move throughout the CFA program. Let's take a quick example here. We've got a distribution, a probability distribution of a company's sales. So look in that far right column. We don't know what those sales are going to be during this course of the next year. They might be 50, they might be 40, they might be 30. So what we have to do is say to ourselves, oh, let's just hope for the best and hope that we sell 50 million in sales next year. No, of course you can't do that. What you must do as a good financial analyst is assign probabilities to those potential sales. So I always tell my students the following. I say, look, rank these from high to low, which we've done in the far right column, and just think of them as best case scenario, 50, worst case scenario, 30, and then anything in between. In this case, we only have one middle sales, but you could have 10 or 20 or 80 of them. Think about putting this together in an Excel spreadsheet. So we assign those probabilities based on things like, well, what happens to the economy, right? If the economy expands, then we'll probably be able to generate more sales. If the economy contracts, then we'll probably be able to generate fewer sales. So probabilities can be based on things like GDP. They can be based on things like our marketing campaign, quality of our board of directors, quality of our sales force, quality of our supply chain, qualities. So you get the sense that those probabilities are tied to the potential outcomes. So that far right column, we have a distribution of sales. When you combine the two columns, we have a probability distribution of sales. So all we're trying to do is find the midpoint. Can you guys see that if I point at my screen? I guess it looks like I'm pointing at you, but I don't mean to point at you. All we're going to do is take the average. And what did we say in that previous slide? It's a probability weighted. So all we're going to do is we're going to say 20% of 50, 30% of 40, 50% of 30, and we're just going to sum those. So our expected sales is 37 million. Think about what this means. That's our average, right? That's our point of central tendency. It's our expected value. So we need to make decisions today based on the expected sales of 37 million. Now we know this is a distribution. We know that when we estimate that 37 million, we know we're going to do it with an error. We know we're not going to be perfectly 100% accurate every single time. So what do? We compute the variance and the standard deviation. This is a measure of the degree of error. How wrong could we be? I mean, think about it. If we expect sales of 37 million for this coming year, and next year we have 1,000 million of sales. We were super wrong. I mean, we're happy that we had generated all those sales, but we were super wrong. That's going to translate into a high standard deviation. All right, so how do we do this? Well, the same way that we did it back in the previous learning module and the same way that we did it here on that previous slide. We're just going to probability weight it. All right, so look down there. What are we doing? The probability that we get 50 times the difference between 50 and the expected sales. So that expected sales figure in there, that's the 37 from the previous slide. And then we square it. So we do all the math. And I encourage you to go ahead and pause the recording and do the math so that you can get that $61 million in variance. And then hit your square root button and you get, what's that, about 8 million. So what are we doing here? We're saying something like, let me go back here. We're expecting 37 million, but on average, we're going to be wrong by about 8 million. So think about how that contributes to our planning for the next year in terms of putting together not just an income statement, but a balance sheet and a cash flow statement. We expect 37, but on average, we're going to be wrong by 8 million. On average. That doesn't mean we'll be wrong by 8 million during this coming year, but if we do this a million times, on average, we'll be wrong by 8 million. Now compare that if for some reason we would have gotten a standard deviation of 2 million. Oh my gosh, now we're pretty accurate, right? A lower standard deviation means that we expect 37 and we're pretty confident that we're going to get around 37. But if our standard deviation is, let's say, 18 million, boy, then we expect 37, but we have no idea what's going to happen, right? So high standard deviations imply a super unknowledge of the future. I'm not quite sure if unknowledge is a word, but you get the point. All right, moving to a probability tree. So look down on the left side of the box. Notice we start at time period 0, and then we can either move up or down. And then after we've moved up or down, we can either move up or down again. This is called a decision tree, and it has tremendous applications, especially for valuing options and valuing bonds that have embedded options. So you are going to see this multiple times in level 2 and in level 3. I'm guessing that the Institute is very likely to test you on this at those later levels under derivative securities than it might in this particular example. But what this does is this gives us an additional understanding of risk. So here's the traditional example that textbooks and professors use all throughout the world when we're starting to explain a decision tree. Suppose we're tossing a coin, right? You toss it, it can come up heads, it can come up tails. And it has a 50% chance because there's only 2 possible chances, right? So notice at first toss, we have a 50% chance of getting heads and a 50% chance of getting tails. Then we have a second toss. That second toss, we also have a 50% chance of getting heads and a 50% chance of getting tails. But here's what this visual representation of all future outcomes, this tree diagram tells us, that we can ask ourselves the question, what's the probability of tossing 2 heads together? Well, you just multiply 0.5 times 0.5. Look at the middle column out there. There's 25%. So heads, 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 tails, tails, heads, tails, tails. They each have a 25% probability of occurring. So think about what's happening here. You have a first toss and then a second toss. After that second toss, you have a whole bunch of outcomes, and you can assign a known probability of those outcomes. Now, what does this mean for our previous examples? What did I say earlier? Dividend yields or stock returns. What we can do is we can take a share of stock like Procter & Gamble, and we can say something like today, the stock price is, let's say it's 100. It could either go up or it could go down. What's the probability of it going up? Well, maybe it's 50%, maybe it's some other percent. We'll talk at length about that, especially when we get into level 2. But then suppose that the stock price goes up during that first day. What about the second day? So what's the probability that Procter & Gamble will rise 2 consecutive days? Well, we use this decision tree to visualize those kinds of outcomes. Now, each of the tree has a branch. And so you can assign a probability to each of those branches. And so we get into really, really cool conversations about things that sound like this. Procter & Gamble, let's suppose, has a 50% chance of going up or down today. So at the end of today, it goes up. But then overnight, Procter & Gamble announces that it has just introduced a new product line. Now, those of you who have sons out there, you will know that once they hit a certain age, even after they take a shower, they still come out smelling. So Procter & Gamble has developed a bar of soap that's going to defunkify teenage boys so that they don't smell. So everyone says, wait a minute, I have sons who smell. I'm going to go buy this product line. So overnight, well, what happens? Well, that probability is no longer 50% because people are going to flock to Target and Walmart and all the retail stores and buy this product line. So maybe it has a 90% chance. So you see how cool this can get. This super simple example where we just toss a coin can lead into much more intricate, much more sophisticated, and much more meaningful as financial analysts so that we can make better decisions for our client, right? We're never going to toss a coin when our client says, here's a bunch of money, go ahead, toss the coin. Oh, heads, we invest over here, tails, we invest over here. That's not why we're in the CFA program. All right, so let's go ahead and work through an example. What the learning module does for you is that it provides a series of super complex equations. And I'm going to work through an example and we'll show you just how simple this is. But let's go ahead and read through some of these things. What does a conditional expectation mean? It really just means something like the expected value of a certain kind of an investment, like Procter & Gamble, given a certain set of real world events, a new product line with this soap. So those expected values, I was saying this earlier, right? Actions of GDP, actions of governments, whether it's changes in money supply or fiscal policy, changes in financial institutions. Go back to the beginning of 2023, we had the collapse of SV Bank. What does that do? Well, that puts all kind of other regional banks on notice. So if we go back here and we try to do this decision tree, we're trying to predict whether regional banks are going to increase or decrease in price during the course of a day or a week or a month. Well, that SV Bank debacle, that happened on a certain day. Well, that changes stuff, right? That changes these probabilities. So look down at the bottom. All we're going to do is we're going to say something like, we're going to sum those probabilities, right? And what we're going to do is these probabilities now, notice that there's a slash sign. So the probability of X, dividend yield, stock returns, whatever that is, given some kind of an event or a change in scenario. That's what the notation for S is. So the probability of X given some scenario. Maybe that scenario is SV Bank failing. Maybe that scenario is spike in inflation. Maybe. Yeah. So we can do all that stuff and we can incorporate. Oh, so you should be thinking, wait a minute, Jim, how do I process all of the macroeconomic variables out there into a simple decision tree? And well, that's a challenge. All right, so let's take a look at a quick example here. We want to predict recovering principal for a defaulted bond issue. And that defaulted bond issue depends on two economic scenarios. All right, so notice that we have scenario 1 with a probability of 60%. We put that in red. Scenario 2 with a probability of 40%. So let's not worry too much about what scenario 1 and scenario 2 are, but maybe they are things like changes in GDP. Maybe they are things like SV Bank default. Maybe they are whatever we come up with. Notice that 60 and 40, they add to 100%, right? So scenario 1 and scenario 2 have a 100% chance of one or the other occurring. Now, once we hit scenario 1, then we have another branch on the decision tree. we might get 80 cents per $1 and we might get 70 cents per $1. So we assign probabilities, 35% to the 80 and 65% to the 70. All right, you see how this decision tree is forming. Scenario 2, well, we might get 60%, we might get 60 cents or we might get 30 cents. All right, so scenario 1 is obviously better for us if we're one of these defaulted bond holders. Scenario 2 is worse for us. So we have a 70% chance of 60 and a 30% chance of the 30 cents, right? So what is the conditional expected recovery? So what we're trying to do here in this case, let me go back real quick. What we're trying to do is come up with the column of HH, HT, TH, and TT. All right, so all we're going to do, we're going to use that equation down at the bottom of the blue box. Are you ready for this? So there's our decision tree. All we're going to do is we're going to say we have a 35% chance of getting 80. We have a 65% chance of getting 70 cents. So there, under scenario 1, our recovery is 73.5 cents. So look on the left side of that first equation at the top of the gray box. The expected recovery given scenario 1 is 73.5 cents. The expected recovery given scenario 2 is 51 cents. So all we're doing is computing kind of like a future value. It's not really a future value, but it's kind of like a future value. Then what do? Well, then we go ahead and say, let's keep coming backwards. And we call these unconditional expected values. There's the formula down there. All we're going to do is, here's the same thing that we had before, the unconditional expected recovery is closest to. Well, now we're just going to say we have a 60% chance of scenario 1 under which we'll recover 73.5 cents. We have a 40% chance under scenario 2 of recovering 51 cents. So you just, are you ready for this? Probability weight those future outcomes. So our recovery is 64.5 cents. That is the very likely question on the exam, not the compute the 73.5 and the 51. You'll have to compute the 73.5 and the 51 in order to get to that 645. This is a great exam question. What does this do? This gives us an expected value, right? So we expect to recover 64.5 cents, so we can make decisions today based on what we expect to happen in the future, given our estimates of probabilities and our understanding of scenario 1 and scenario 2. Let's go ahead and look at this last LOS in which we ask the following question. Let's suppose that during the course of our decision tree that the information set changes. Think about how valuable that new information is. So this is this idea of Thomas Bayes. Notice what we have there in that very first point. Updated or posterior probability. Given a set of prior probabilities, it allows us to update our decisions. So think about our decision tree in that last example with Procter & Gamble. And then Procter & Gamble decides to do something else, and then the economy changes, and then so we have all of these changes. And how can we explicitly measure those updated probabilities? The example that I've been giving to my class for the last, what has it been now, 2 years or so, is the following. You guys should know that I'm a huge James Bond fan. I saw my first movie. My dad took me when I was 5 years old, 1966. Anyway, when Daniel Craig announced that he was going to, this last movie was going to be his very final episode, his very final role, of course, we're trying to figure out who is going to be the new James Bond. Well, you can use this Bayes formula to kind of figure this out, to estimate the probability that an individual actor will get that role. Just take a simple example. Suppose there are 5 dudes out there who are in the running. So you could just say something like, well, each has a 20% chance of getting the role of James Bond. But then over time, what happens? You hear all these rumors. So maybe one of these actors marries a famous country music star, and that changes his probability. Maybe the producers of James Bond, maybe they want their James Bond actor to be married to a country music star, or maybe they don't. So that might increase or decrease his probability. Heaven forbid, remember what happened to Luke Skywalker in between the first and second movies. He was in an accident. He needed to have some plastic surgery. Maybe one of these 5 dudes has an accident, heaven forbid, and, he can't perform all of the running and jumping and all the cool stuff that James Bond has to do because, broken arm, broken leg, whatever that is. Or maybe. I mean, you have all these probabilities. And so as the James Bond decision-making process evolves over time, you can update these probabilities. Now, I'm always fascinated by the way finance textbooks and finance people try to explain the statistics behind all of these kinds of models. And the Institute really is no exception. And I'm not being critical at all. There's really no way around this. Excuse me. What you can do is you can take a look at the very bottom blue box. Here's our summary of this Bayes formula. We're going to try to estimate the probability of an event given some information. And we can adjust some things over on the far right-hand side of the equal sign. But notice we have probabilities in there in the numerator and the denominator. What that means is that we need to go back to our quantitative methods beginning. So look at these equations here. I'm not going to suggest that you memorize these things. Remember, we've got things like Venn diagrams and unions and intersections, and that's what all this stuff is, using conditional probabilities, which we just used in a previous example, the total probability rule, which we did before. And so here are the variables that are super important. The probability of B sub I. These are known prior probabilities. The event A is some event known to have occurred, and then the probability of B given that event is known as the posterior probability. So keep in mind that these are all good equations. These are all good mathematical stuff for you to know. Here's the good orange and blue box for you to remember kind of general formulations, but let's work through an example and you'll see how simple this is. Now, here's my advice. This example and the example in the body of this learning module both ask a similar question here. Notice at the bottom, what is the probability that there's a negative return on the New York Stock Exchange? This is a very similar question as in the body of this learning module. So it's very likely that if the Institute asked you this question on Bayes, it's going to be in this context. Now, I will also say to you that when you look at the problems at the end of this learning module, there's only 2. One asked you for the mean, one asked you for the standard deviation. So there are no problems on any of this stuff that we've done over the last 10 minutes or so. I'll let you decide whether or not you want to spend extra time on these things. My advice is to spend the extra time because, as I say regularly throughout all of my recordings, is that every LOS is a potential exam question. But we can also infer from the problems at the end of each learning module what kind of importance, which topics are important to the Institute. All right, so enough of my babbling there about what can show up and what can't show up on the exam. All right, so we have an analyst investigating the performance of stocks on different exchanges. All right, so 50% come from the New York Stock Exchange, 30% from the London Stock Exchange, 20% from the Tokyo Stock Exchange. Now, when you get to a problem like this, I think it's easy, and it might be just the way I think, but I will visualize that in this number, there are 100. So 50 from the New York Stock Exchange, 30 from London, 20 from the Tokyo. All right, so what are we doing here? We've got 100 stocks. Think about them as 100 little ping pong balls in a swimming pool. So we're going to reach in and we're going to grab one of them out. All right. Now here's this updated information. The probability of a stock posting a negative return is 40, 35, and 25% on each of those exchanges. So what we want to do is we want the probability that when we pick out a ping pong ball from the swimming pool, that it's going to have a negative return. So wait a minute. If we were to say something like, look, if we knew that the ping pong ball was New York Stock Exchange and we pick that out, well, then we would know that that probability is 40%. Similarly, London, 35%, Tokyo, 25%. But here's the deal. Ready? Look at the question. Picks a stock at random. So the ping pong balls in the pool are not colored by the type of exchange. They're all white or yellow or pink or blue, right? We don't know which ones are New York, which ones are London, and which ones are Tokyo. So how do we figure out that probability that that randomly selected ping pong ball is going to have a negative return? So let me just go back here quickly. All right, so look down at, well, let's go back to the orange box. So probability of the new information given the event, that's going to be in our numerator. So there's probability of the information / given that event. All right, so here we look at the bottom here, probability of A / B sub I. All right, you ready for this? So this is super simple. So what do we know? We know we have let's go back here. We know we have a 50% chance of picking a New York Stock Exchange ping pong ball, which tells us that then we're going to have a 40% chance of posting a negative return. Well, there's our numerator, right? 50% times that 40% chance, right? That's the numerator. Then all we're going to do is divide by all of the other possibilities, right? We're trying to do a probability. So in the denominator, we take the 50% times the 40, that's New York Stock Exchange, 30% times the 35%, that's the London Stock Exchange, and then 20% times the 25%, that's the Tokyo Stock Exchange. So do you see how this Bayes formula, it kind of takes away from what we've done during this entire slide deck, but it puts it in a numerator and a denominator in a form so that we have this updated information. So there you go, 56.3%. And then, of course, my advice for you is to go back and change the question, say, probability that it has a negative return on London. Do that one. Probability of negative return on Tokyo. Do that one so you get the sense of what's going on here. Then what I want you to do is I want you to go back to the reading and work through the example inside the middle of that learning module. So I believe that takes us to the end of these 3 learning outcome statements. This is super fun. What did I say somewhere in there? Statistics and quantitative methods is your friend. So get your arms out, wrap your arms around this material, embrace it and love it and hug it and do all those really, really good things because look, I can warn you now, but you'll see as we move throughout the program, you're going to use this material and it's going to be applied to lots and lots of other different kinds of topics. So what do I want you to do now? I want you to go to the middle of this learning module and work through that Bayes formula. Then I want you to go and compute the expected value and standard deviation and the problems at the end of this learning module. So hey, that was fun for me. I hope it was fun for you. Thanks for watching and good luck studying.